So the past videos we have been studying fluctuations of functions, we've studied limits and continuity, and now we've finally arrived at the main concept to quantify fluctuations. And this concept is called differentiation, and the basics are presented in sections 2.1 and 2.2. To explain what it means, I will go back to our example of the mountain covered by snow. We're sitting on the top, and a helicopter will throw us some packages of food, and this helicopter can do so with a certain degree of accuracy. Suppose the accuracy is of this size, and the package falls, for instance, here. What happens is that on the place with these coordinates, and so it will fall here on the mountain, and well, it doesn't look too badly. We will be able to recover it. Now, of course, the mountain might look a little bit differently. It might look like this. We're sitting here, and we are now in much bigger trouble, because if the helicopter would throw with the same degree of accuracy, so the same spread over here, so like this, and the package would fall at the place with the same coordinates as with this mountain, well, then we would be in really bad shape, because we would never be able to recover it. So accuracy highly depends on, or required accuracy would highly depend on the slope of the mountain. Now, how can we try to describe slope a little bit more mathematically? Well, just saying that slope is something like the change of height per unit. So per unit, per centimeter, per meter, whatever, per millimeter. Now, to really formally define slope, we will first study the example of linear functions. Suppose that we have this linear function, f of x. F of x equals cx plus d. So it's a polynomial of degree 1. How would we define the slope? Well, suppose we're sitting at the point with coordinate a, so we're sitting somewhere here. How would we calculate the slope? Well, the slope of a linear function, you see, it's constant. The change of height per unit is everywhere the same. So how would we do it? We will look at the function value, the height at the place with coordinate a. So this f of a, we would compare it to the height at the place with coordinate a plus 1. We would compare the differences between the function, the heights, and the coordinate values, and we will divide these. So we would divide this difference by this one. Now, since the slope is constant, it doesn't really matter. We can also compare the height at the place with our coordinate a to the height at the place with coordinate a plus h. We compare the difference, that is, do so, and we divide by the difference in coordinates. So we get the difference in heights divided by h, and if we plug in the formula for our linear function, we get, well, c times a plus h plus d minus c times a plus d, and what we are left with is c times h divided by h equals c. So the slope is in fact c, and c is precisely the coefficient of x in our formula for the linear function. So the slope has a very nice and easily computed value over here. Let us give a small numerical example, so if our function f of x is equal to minus 2x plus 3, then the slope would be minus 2. But of course, if we shift this function, so we look at minus 2x instead, then again we get the same slope. And of course this makes sense if you think about mountains, because if we shift the mountain a little bit upwards, so we look at say the bottom from the point of the bottom of the sea, of course the slope won't change really. Now we will make this more precise, and we'll have to study how the slope could be calculated in case our function is not as easy as this one.